welcome you all to this special lecture, and this lecture is in the course phy101 in mechanics, and the lecture is on special theory of relativity. The main instructor in this course, Dr. Sanjeev Kumar, asked me to give this special lecture, and I'm thankful that he's given me this opportunity to talk to the MS20 batch. This is going to be one lecture, a recorded lecture, which will be shared with you. And later on, we will have a discussion tomorrow on Monday on Zoom. And there will also be a follow-up lecture on relativity, which me or Dr. Sanjeev Kumar will give, where we will work out the details. So for the discussion, I expect all of you to have gone through this lecture and some of the things that I will ask you to do. So let us begin by today's discussion by saying that the special theory of relativity as you all know, was developed by Albert Einstein in 1905. And I must tell you that this is not the first theory of relativity. So there is certain motivation behind developing such things, and that motivation is very, very important. The science that we do, the science that you all learn, there is several kind of universality in science. So science is universal. And what do I mean by universal? Let me tell you one kind of universality, that it is same for all human beings. So the way science appears to me is the same way a science will appear to a woman, that the science will appear same way to people belonging to different language groups or religions and so on and so forth. So science is universal knowledge. Similarly, science is same on all locations. Same at all locations. So if I go from here to United States, if I go from here to Ethiopia, I don't change my science. I keep the same scientific principles and laws. So it is independent of location. Actually, it's independent of location in the universe. That's why we are able to send satellites, and we are able to study cosmology and make conclusions about stars and galaxies. They are far away at different locations, but we apply the same laws of physics, and that is another kind of universality of science. The third universality, which is again extremely important, is that laws of the sciences same in all inertial frames of reference. This concept of an inertial frame must have come in this course earlier. Let me mention to you very briefly the idea. The idea is that velocity is relative while acceleration is absolute. Now, velocity is relative means what? It means that there is nothing fundamental about motion. So if I am moving with respect to you, you see me move. From your frame of reference, I appear to be moving, and from my frame of reference, you appear to be moving. Now, who is moving, you or me? This can never be settled, because the motion in itself is relative. So this relativity of motion tells us that if there are two frames and they are moving with respect to each other, or if there are three frames, A is moving with respect to B, B is moving with respect to C with a constant velocity, they all are as good. Each one can think that his or her frame is stationary and others are moving. And therefore, laws of physics should be same in this set of inertial frames. So, what are inertial frames? So, inertial frames of reference are those in which Newton's laws are, in which laws are valid. And these are frames which are moving with respect to each other with a relative velocity v, j, which is constant. So if I have one inertial frame, I can find infinitely many other inertial frames, and that is called a set of inertial frames. So this discussion must have happened in this course. Of course, there are non-inertial frames in which you have pseudo forces, and those forces come into play because the frame itself is moving and accelerating, and so on and so forth. So those are the discussions which would have happened in the course early on. So my point here is that the principle of relativity. So the principle of relativity that we are talking about, let me restate it, that laws of physics are same in all inertial frames. Now, I want to emphasize that there is nothing new about this. It is not that Einstein kind of was the first person to think about it. This was more or less understood earlier, all the way from Galileo it was known, and that's why you had Galilean transformation. So if you write down laws of physics in one frame, how to write down these laws of physics in another frame, how a phenomena occurring in one frame would look to an observer in another frame. So these questions had been more or less formally, informally asked and answered partly. But Einstein put it very directly that laws of physics must be invariant. The second important thing, which is not at all a philosophical or a fundamental position like the first one, is that velocity of light is same in all inertial frames of all frames of reference. So what does this mean? This means that if you have a light pulse which is moving with some velocity in one frame, so this is a pulse. So pulse means it is moving, it's like this. So I start a pulse, and this pulse is moving with velocity of light in, so I have a frame of reference. So I have a frame F, S. In this frame there is a pulse, so it is moving. After some time it reaches here, and like that along x-axis. So this pulse is moving in time, as you see. So there is certain velocity which I call c, velocity of light in frame S. Now what if you are in frame S dash? So you are in frame S dash, so you are a person in frame S dash, and frame S dash is moving in this direction, opposite to this pulse. So pulse is going this way, the frame S dash is moving opposite to the pulse from this side with a velocity v. What does our intuition say? Our intuition says that now, see, how would we think? We'll say, all right, let's start this pulse here. Now, this pulse has to cover a certain distance. It is moving with, say, velocity c. By the time pulse will reach, by the time, you know, this pulse will come, this frame is moving. So in this frame, when it reaches here, this observer would have come here because this is moving in velocity v. So this S dash observer will be here, and therefore this observer will see a larger velocity, which is c plus v, because now you see the distance covered is it has happened faster. But that is not what happens. The velocity of light seen by observer S and this observer S dash is actually same. So this is very counterintuitive, which basically is saying that if a photon is coming towards you and you run towards the photon, that does not really make you and the photon cover distance faster. It's counterintuitive. And where did Einstein get this from? He didn't get it from anywhere. It's an experimental fact. And this fact was established by Michelson and Morley experiment, which is a fundamental experiment in physics, which today I will not talk about, but somebody should do a small summer project, or we can, a full lecture is needed to describe to you how Michelson and Morley established that velocity of light is same in all frames of reference. Now, what Einstein did in special theory of relativity is that he told us how do we go from one frame of reference to another frame of reference and look at laws of physics or equations of physics, as we will see it unfold in a minute, which is consistent with these two things. Laws of physics are same in all inertial frames, and velocity of light is same in all frames of reference. So the beauty of the whole thing is that one is an experimental fact, which is established by Michelson and Morley in through his experiments, and other is a viewpoint that that is very important viewpoint, or a point of view that this is well, you guys are too young, so I don't want to confuse you, but let me make one statement. Let's invert it. After all, physics is not something out there. Physics is something that we create. So it's a knowledge that we create. So we would like to develop or create knowledge about the world which is same in all frames of reference. That is the deeper philosophical connotation of this particular statement. And you see how when a certain philosophical or a theoretical point of view interacts with an experimental fact, and then you create new knowledge, what kind of things come out. Special theory of relativity is a very important example of that. To implement these two in a way that we will see, Einstein had to rethink about nature of space and time, and that's what we will now come to. Of course, if this was an actual class, there would be many questions at this stage, and we will kind of go over those, but all those will have to be postponed to the discussion session, and we will discuss whatever is on your mind when we have the discussion tomorrow. So in the Newtonian way of looking at things, the space-time is a stage on which phenomena happens. And in some sense, in our intuitive mind also, we think about that. Because we look at a room and we live inside the room. We think room is space. There is a clock in my room right in that corner. So there's a clock and there is a space, and I feel that in my office I live in my activity, which is my science, my calculation, is phenomena happening in this stage, which is space-time. So space is this room, time is that clock. So Newton's way of looking at space-time, so space and time is the stage, he says, stage on which phenomena occurs. So in some sense it is in the background. So it's a fixed background, fixed backdrop. Alright. So Einstein started rethinking about it. Apparently in his memoirs he writes that he was uncomfortable with this from very early on, when he was 15, 16, maybe your age or even younger. So let me tell you, let's see, how do we measure time? How do we think about time? When I say that clock is measuring time, so how do I look at time? So there's a day, I divide the day, there's a sunrise, there is sunset. What happens in between? Well, I got up, I looked at someone, that's another event. I had ate something, that's another event. I went to class. So I punctuate the sunrise and sunset, my whole day, with events. Alright, so this whole notion, so where is time? What happens between two events? So I got up and then I did something. What happens between those two? I will say, oh, I did that. So I will always put another event. And then I say, all right, between these two, I didn't do anything, but 5 minutes passed. What are these 5 minutes? 5 minutes are that the minute hand of the clock went from 5 to 10. Well, that's an event. The minute hand was at 5, then it went to 6, 1 minute. Inside 1 minute, what happens? Oh, I say 60 seconds. But what are those 60 seconds? Those 60 seconds are the second hand went from 1, 2, 3, 4, 5 to 60. But that's again events. It is something happening. What happens within a second? I will bring in another clock. Alright. But that clock will also have events. Then I will bring an atomic clock. So, where is time? Finally, if I am not able to put an event between two very close events, I cannot say how much time is elapsed. For example, can I prove that the first second is equal to the second second? That's an assumption. So, this discussion can take us very far, but the point Einstein makes is that events are important. They are primary. Phenomena is primary. So events are important or primary, and time is a relationship between events. So time is a relationship between events. So I can order, I can say that E1 happened before E2, that happened before E3, that happened before E4, like that. What happened between E1 and E2? How much time elapsed? Only way, say E1 happened here, E2 happened here. So now, only way I can do is insert another event, E dash, and then I can insert events, and then I can order those events, and then I have to make an assumption that my clock runs at constant rate, and therefore when I insert certain number of seconds between two events, that measures the time between those events. But all I am really doing is putting in more events within a time interval, what I call, and counting those events and assuming that I am actually measuring time. So time is a construction. I have constructed a certain notion called time and then made certain assumptions about some phenomena having periodic phenomena and each period having same time, and then relative to that I can measure everything else. So once I define a unit and I assume that unit is uniform as I move into future, that's an assumption, then I can measure time. So measurement of time is an abstraction which is derived from sequencing events and inserting other events into those events, and then assuming that certain events are happening in the same way at a constant rate. You see how different this perspective is from a universal time which is flowing and everything is happening in time. Similar arguments can be given about space. So instead of thinking about objects in space, there are objects, and then there are relationships between objects, and those relationships may be that if I send a light signal from one object to another and it reflects back, how much time it takes. There are many objects around, and those many objects, when they interact or I exchange light between them, certain time is taken, I assign certain distances, and between two objects I can put in a third object. So that is how I map space. So like time is a relationship between events, space is a relationship between objects. And these two things are also related with each other, because here I was talking about events as time events. But events, as we will see, of course event will happen somewhere. So event will be at a location. So event will have a location. So in a general way, when I say event will mean something which happens somewhere. So what Einstein showed us is that events are primary, events are important, and the rest can be derived from events. So let us now define an event, and so let's assume that we have a frame of reference which I will call S. So I have a frame of reference S, and in this frame I think of an event. So what do I mean? Something happens somewhere, like there is spark of light, something breaks. So any event is like that. So let me call this as event E. So it happens at some time t, at some location x, y, z. So this is how I define an event. So event has a time and it has location. So event, something happens at an instant, at a location. Immediately if you think a little bit further, you see that it's a very powerful concept. What is motion? So this course is mechanics, it has been about motion. So if something is moving, it is a sequence of events. That's how you will perceive it, because something, after all, something is moving. So let me look at it stroboscopically. What does that mean? I shine light on it periodically and see it's here, it's here, it's here, it's here, it's here, it's here, it's here. So it's moving. And each time I look at it, that's an event. So it's a sequence of events. From the sequence of events, I can assign velocity, acceleration, calculate those properties. I can think about forces, because forces will influence events. Those are the kind of, so all mechanics can be recast in terms of events. All right. But we also, so you see in the event, so I'm not doing any relativity, I'm doing regular mechanics. So there's time, there is space. But if there is a fundamental velocity, which is a universal fundamental fixed maximum velocity, which is velocity of light, which is called c. We give it a symbol c. It is about 3 lakh kilometers in vacuum, by the way. Velocity of light in vacuum, it is about 3 lakh kilometers per second. Distance from Earth to Moon is about 3 lakh kilometers, so light can travel that distance in about 1 second. And this velocity is a fundamental constant of nature. Then immediately you see that if this is a fundamental constant, then I don't really need to use separate units for space and time, because I can, if I say Ct, now Ct will have dimensions of length. So instead of measuring time, I can say, oh, time, length traveled by light in that much time. So instead of saying 1 second, I will say 3 lakh kilometers. 3 lakh kilometers if means light travels that in 1 second. 6 lakh kilometers for 2 seconds. So I don't have to use separate units and separate dimensions for space and time. So an event can be described like that. I just multiply this by c. Then there is another useful notation. What we do is, as you will see, that space and time are going to get mixed up very soon. Already you see that time can be measured as length, and then therefore I give it the name x0. And x coordinate I call it x1, and then the y coordinate I call x2, and z coordinate I call x3. So instead of calling an event t, x, y, z, I call it x0, x1, x2, x3, where x0 is equal to Ct, x1 is equal to x, x2 equal to y, and x3 equal to z. And in the relativity notation, for example, in the relativity notation we will call it x mu. So x mu, where mu is equal to 0, 1, 2, 3. So this is time, and these are the three space coordinates. Some of this notation is very useful because when you read books and all that, immediately whenever you put a Greek symbol in the superscript or subscript, that is supposed to have this 4 indices, 0, 1, 2, 3, where 0 is time and 1, 2, 3 is space. Some older books will use 1, 2, 3, where fourth coordinate is time. So that's a matter of convention. All right. Now, of course, so this is just notation. So I can think about object which is moving. So object which is moving, let's assume that object is moving along x-axis. So then I will say, all right, in regular mechanics, I will say that what happens, x, that is the coordinate of that particle which is moving along x-axis with the velocity. I will say that x at time x0, so x at t is equal to what? It is x, the initial value, and it is moving, so plus I will say x1 into x0 by c. So I can write, so this is same like saying x of t is equal to, sorry, not here, should be here, so this is x initial, x initial plus vt. So, what did I do there? So vx0. All right. So this is how. So because this is ct, so that c factor is coming and redefining things over here. This notation you will see will be very useful as we move on. So we can describe everything in terms of events and this kind of notation. Now what are we after? What we are after is that if I am able to translate events from one frame of reference to another frame of reference, then I can examine my laws. Because laws are a relationship between events, how something is moving. If an object has accelerated, then the events of its presence at different locations has changed, it has become faster or slower. All that is encoded in events, and these events can be observed in one frame or another. So let us think of a frame S and a frame S dash, and in the frame I will think of a clock, so that I can measure time. So this is the clock showing time here and showing time here. T, which of course I will call it x0 very soon. So x0 t. So the a frame of reference is a three-dimensional. But it is a three-dimensional. I call this as x, and this is if this is x dash, this is y dash, and z will be coming out of this board. All right. So this is x, this is y, this is z. So there is a frame, and in this frame, what I have is a clock. And for simplicity, I will, after all, this one is moving with a velocity v in the positive x direction. So now you see this is frame S, this is frame S dash. This is inertial, this is also inertial because this is moving with a constant velocity with respect to S. And this would have come, so this is the origin. So there is an observer I can think of here. So I can think of an observer here and an observer here. This one is sitting at this origin O, this is sitting at this origin O dash. For simplicity, we will assume that when this observer came from this side and when their origins coincided, at that time we put t equal to t dash. So clocks, because clock is something that we can synchronize, we can move and set it 0. So when they met, they shook hands, they also synchronized their clocks. After that, of course, S has his clock and S dash has his clock. Alright, so this is the situation. I hope I am clear. So, and this guy observes phenomena, this guy also observes phenomena. This guy develops his laws for phenomena, motion. This guy develops his laws, phenomena, motion. They are similar: minds, brains, notebooks, resources. Only thing is that S dash is moving with a velocity v along positive x direction with respect to S. Alright. Now the question is, an event happens here in this frame. Alright? And that event I call E. This event, event happens, why should I say in this frame? This event happens and it is seen by S. And S assigns the observer in S, whose region I have put as O. Observer O living in S assigns this event certain coordinates. And this is, what are the coordinates? T, X, Y, Z. I'm just using older notation so that you don't get confused. This we will write as E, X0, X1, X2, X3. Alright? And same event is also observed by S dash, the O dash living in S dash. And therefore this event is assigned another set of coordinates. So this is O, observer O in S assigns event E these coordinates x0, x1, x2, x3. Observer O dash living in frame S dash assigns another set of coordinates which is T dash, X dash, Y dash, Z dash, and that is equivalent to E, x0 dash, x1 dash, x2 dash, x3 dash. So what are we interested in? We are interested in how these, so how this set, so the question, the question is how are the coordinates, of E in two frames related. So this is the question we need to answer. Of course, Galileo gives us a way. So there are Galilean transformations. What are Galilean transformations? Galilean transformations tell that T is equal T dash equal to T. So let me write it like this. X dash is equal to x minus Vt. Y dash is equal to y. Z dash is equal to z. This is Galileo, which you would have seen. So this is Galileo's principle of relativity. I also want to emphasize that this also tells you how events in one frame are related to events in another frame. Alright. Okay, so this can be written in this notation as x0 dash is equal to x0, x1 dash is equal to, you have to be little careful, x1 minus v by c x0, and x2 dash is equal to x2, x3 dash is equal to x3. Now what happens is that if you use this principle of relativity, this principle of relating events from one frame to another, what happens? What happens what I showed you in that pulse experiment, that velocity of light will not be constant. So light pulses, so what happens, this is the velocity of light will change. Right? So if there is a light pulse is like any object which is moving. So if there is a light pulse moving as we saw, well, that velocity will change. It will become, if the light pulse is, so this frame is going this way, if light is coming from this direction in frame S, this will become C plus V. If the light pulse is going this way, it will become z minus b. So light is like any other object, and if you run towards an object, you reach faster. If you run away from that object, you reach slower. So Einstein's way of relating these events was different, and of course that is a way to relate events in one frame to events in another frame, which respects the fact that velocity of light is constant in all the frames. And let's see what that transformation law is. These are called Lorentz transformations, which also tells you that another person was involved here by the name Laurent. And Laurent had written down these equations without really putting it in this perspective, which Einstein put it. Therefore, we call it Einstein's special theory of relativity. So these are Galilean transformations, which in some sense is Newtonian relativity, and then we have Lorentz transformations. So what are these Lorentz transformations? How do we relate events in S and S dash so that we are consistent with the fact that velocity of light is same in all frames of reference? And before I do that, let me define two parameters. So so best way to measure velocity is a dimensionless parameter called beta, which is v by c. So since c is a fundamental constant of nature, which is the velocity of light in free space, so we say, instead of saying something is moving with 1 lakh kilometers per second, we say, oh, it's moving at the velocity 1/3 of velocity of light, 1/10 of velocity of light, 1/millionth of velocity of light. So we just measure velocity as a fraction of velocity of light. And in terms of this, another important parameter is gamma, which is 1/1 minus beta square. So these two dimensionless parameters are very important in this over here, and we can write down things in a very nice compact way in terms of these parameters. All right. So what is the how do things are related? So I have x0 dash is equal to gamma x0 minus beta x1, and then I have x1 dash is equal to gamma x1 minus beta x0, and x2 dash is equal to x2, and x3 dash is equal to x3. So these are Lorentz transformations. So you immediately see that when velocity is small, gamma is 1 and beta is small, and therefore you see that they become Galilean transformations. So our word, so this the non-trivial nature of this. See, first of all, this is very different from here. Here, time was completely independent of the space coordinates. Here, the way time coordinate or the first coordinate, the way it is moving, or where this clock is marking events, is now becoming dependent on space. So space-time are getting mixed up with each other. But that mixing up, and also you see there is certain scaling which is happening due to gamma. All this happens only when velocities are high, not small. If velocities are very small compared to velocity of light, this equation and this set of equations, are same, very similar. The effects are very small, but when velocities are large, then you begin to see these effects. Alright, so as we work out, one can look at those details. A very compact way to write this is in the matrix form. So we can write x0 dash, x1 dash, x2 dash, x3 dash as a matrix multiplying x0, x1, x2, x3, and this matrix can be written gamma minus beta gamma 0, 0, minus beta gamma gamma 0, 0, 0, 1, 0, 0, 0. Alright, so these are Lorentz transformations. So I can write down how events are related in S and S dash. If S was moving along y direction, then what will happen? Then this equation will look like this equation, and here I will say x1 dash is equal to x1. Similarly, if the frame is moving along S dash is moving along z direction, then this equation will be like this equation, whereas these first two will be x1 dash is equal to x1 and x2 dash is equal to x2. So this is how it works out. So in principle, if S dash is moving in some third direction, then I can first rotate my frame and then apply a Lorentz transformation. So all those are details which come as you study relativity further, but the fundamental nature of things gets all the non-trivial and fundamental things come through by this situation where S dash is moving with a constant velocity along positive x direction. So in this notation now, so I should write V is equal to beta into C, right? So beta is the parameter which defines things from between these two frames. Now there are a lot of consequences of Lorentz transformations which one would like to look at, and let me point out some, and then we will see how we go about these in discussion session and then in the follow-up lecture which we will do. But let me tell you what happens. So you just take these Lorentz transformations seriously. So then we should use them to establish various things. So number one, if there is a rod in this frame S of length L, the rod, so well, I should not say length L, there is a rod here, and S measure in the O living in S measures its length to be L. Now the observer O dash in S dash can also measure the length of this rod, and that turns out to be L dash. And what you can show is that L dash is equal to L by gamma. So which will be less than L. So this is called length contraction. So as we saw that, as I said earlier, for Einstein this was not at all surprising, because length is something we abstract out. Rod is there, rod has two ends. We map those two ends, and the difference between those two ends we call length. And that process, if carried out in two frames, gives you different answers, and this is how these two answers are related. We will work it out, or you will work it out using the Lorentz transformation. The second is that two events happen, E1 and E2. E1 and E2 are two events, and in frame S we measure delta t. So delta t is the time difference between these two events. So delta t is equal to time difference between E1 and E2 in frame S, and delta t dash is time difference between these two events in frame S dash. And then you will see that delta t dash is equal to gamma into delta t. So this is called time dilation. So time gets dilated. So two events seen in S dash will appear to take place, the time difference will appear longer. Longer means what? If you use the clock in the frame S dash, more seconds or minutes or hours will pass between these two events compared to S. This will take some time for you to internalize completely how it happens, but this is a consequence of Lorentz transformations, and these things have been measured experimentally. A third very important consequence is that two events even E1 and E2 which are simultaneous in S may not be simultaneous. May not be simultaneous in S dash. It's also so however, causality, as you will see, as the subject of relativity will develop, causality will be respected. It cannot happen that something occurs before event E1 occurs before E2 in one frame and it occurs after. That kind of causality cannot be violated. However, two events which are simultaneous in one frame may not be simultaneous in another frame. So we will work out these things and maybe many other consequences of Lorentz transformations. But to end this discussion today, let me mention that things which do not change from one frame to another frame, so like length changes, time interval changes, so there is something we define as interval, okay, or proper interval, which is defined in the following way. So I define delta tau square is equal to delta x0 square minus delta x1 square plus delta x2 square plus delta x3 square. So if I define this quantity, which we call interval, it is related to time. It's a combination of time difference and length difference between the two events. So I have E1 and E2, and this is delta t is an interval between E1 and E2. So it's a definition. I'm defining. You can show by using the Lorentz transformation I wrote down for you that delta tau dash is delta tau. So this particular quantity or this particular relationship between these two events does not change whether you look from one frame of reference or you look from another frame of reference. So such objects are called Lorentz invariants, which look same from different frames of reference. Alright, so well, we have just started the subject. So the subject of relativity basically means that we take Lorentz transformations and work out their physical consequences. Then of course, so one is consequences. And second is that since laws of physics are same in all frames of reference, we should be able to write them in a way which is Lorentz covariant. Which means the fact that laws of physics are same should come simply, very nicely, naturally. The way we should write them in such a way that this comes very naturally. And that the notation I was developing for you in terms of matrices and all that comes in very handy. That is not, that will go a little too far and you will do it maybe in another course, but in tomorrow's discussion and in day after's follow-up lecture, we will focus on working out some of these things so that you see that this is actually happening. And I will emphasize that to come to terms with this somewhat non-intuitive or counterintuitive consequences, you should always go back to Einsteinian thinking, where space and time are abstractions, constructions that we have developed or constructed to understand phenomena, whereas events and what actually happens is fundamental. And that has certain laws which we create, and those laws are such that they have to remain same in different frames of reference. And somehow it is so that light is special. That first of all, nothing travels faster than light, and light velocity is same in all frames of reference. So that particular fact about the universe in which we live, combined with our background thinking, gives us all this beautiful physics.